The Kerr metric defines the curvature singularity as a ring at the radial coordinate of 0 and the equatorial plane of pi/2. This ring bounds a regular, finite region of the central surface, known as the disk. Because this central disk is regular, we have to determine if test particles can traverse it, or if it acts as a terminal boundary for all matter. This phase space plot tracks particles through the separated geodesic equations. At the exact moment the radius reaches 0, the radial potential r of 0 is determined by the term -a² times q, where q is the Carter constant. For a particle to cross the disk transversely without hitting the ring, the radial potential must be positive. This requires a negative Carter constant. These q-negative trajectories reach the disk in finite proper time. The affine parameter remains finite, meaning the particle arrives at the central surface without encountering a curvature barrier. Truncating the space-time at this disk without providing a continuation law results in geodesic incompleteness. The particles arrive at a coordinate boundary that has no geometric reason to stop them. This topological map illustrates the Boyer-Lindquist analytic continuation. It extends the radial coordinate r through the disk to -infinity, creating a second asymptotically flat region on the other side. In this second region, the asymptotic expansion of the metric component GTT takes the form -1 minus 2m over rho. Relative to the stationary killing field continued from the first sheet, the ADM mass of the second region is -m. To avoid a negative mass universe, we might attempt to manually glue a second positive mass Kerr exterior across the disk instead of following the analytic path. The Boyer-Lindquist continuation is analytically smooth, but results in a negative mass sign. The positive mass alternative avoids the sign flip, but it encounters a geometric obstruction within the matching conditions of the disk. To find that obstruction, we must analyze the local metric of the regular disk on a constant time slice. Setting radius to 0 and time to a constant, the 4D metric reduces to the flat polar metric, d rho squared plus rho squared d phi squared. The disk is intrinsically flat, behaving like a standard Euclidean plane with no conical apex. However, this spatial slice is only one part of the geometry. Over time, this disk sweeps out a three-dimensional time-like world tube. While the spatial disk is flat, the way this world tube is embedded in the full four-dimensional spacetime is not. We measure this embedding using the second fundamental form, KAB. A direct calculation at r equals 0 shows that the time and angular components are non-zero and depend on the mass and rotation of the black hole. The intrinsic flatness of the spatial slice does not imply that the world tube is extrinsically trivial. This non-zero extrinsic curvature determines if two regions can be joined smoothly. We can now test a reflection gluing of two identical positive mass Kerr blocks across this world tube. The first Darmois condition requires the induced metrics of the two boundaries to match. Since both sides are intrinsically flat, this condition is satisfied. The second condition for a vacuum matching requires the extrinsic curvature to be continuous across the junction, meaning the jump in KAB must be 0. Because we are mirroring two identical blocks, their outward-pointing normals are directed oppositely relative to the common coordinate system. In this reflection, the jump in extrinsic curvature does not vanish, it doubles. Since the second fundamental form is non-zero, this jump prevents a smooth vacuum matching. A reflection gluing of two positive mass Kerr blocks cannot satisfy the requirements for a C1 vacuum spacetime. Failing the vacuum condition means the geometry is reduced to a C0 distributional spacetime. The extrinsic curvature discontinuity creates an Israel surface tensor, a stress-energy layer holding the two spacetimes together. This tensor diverges to infinity as we approach the singularity ring at the disk edge. Beyond the static matching conditions, any continuation must also be evaluated against the dynamics of a collapsing star. Interaction between ingoing and outgoing radiation leads to mass inflation, an instability that exponentially grows at the inner horizon. A positive mass continuation requires either this divergent material shell at the disk or a branching structure that causally isolates the disk crossing from the region of mass inflation. The local vacuum equations govern the geometry near the disk, but the global topology and time orientation are independent inputs. We must choose between different axiom sets. The Boyer-Lindquist continuation is mathematically smooth, but creates an asymptotic negative mass. A one-ended model avoids the second region, but leaves the disk as an incomplete boundary. A same-time positive mass model introduces the divergent surface tensor we calculated. A fourth possibility is the time-reversed positive mass completion. This model treats the sign change across the disk as an orientation effect, rather than as a literal negative mass source. In this time-reversed map, crossing the boundary reverses the stationary killing parameter. The first sheet's future generator becomes the negative generator on the second sheet. Because the Komar mass integral is linear, replacing generator x with negative x flips the calculated charge's sign. The mass remains positive relative to each region's own future-directed generator. The Boyer-Lindquist sign flip is interpreted as a consequence of this reversed orientation. This resolves the mass problem at the cost of global time orientability. The connected two-sheet manifold becomes subject to chronology violations and closed time-like curves. Choosing a continuation is a trade-off between the analyticity of the negative mass sheet and the physical requirement for a positive mass interior. A rotating black hole does not offer a simple vacuum continuation. Traversing the singularity requires explicit global axioms to bridge the gap between mathematical smoothness and physical stability.